me, Sir Ernest, and today we're going to solve problem 2.34c of Griffiths 4th edition. The problem reads, find the energy stored in a uniformly charged solid sphere of radius r and charge q, and do it in three different ways. So in the previous videos, we've already answered this problem for letters A and B. So in this case, in our video today, we're going to solve this problem using equation 2.44. But what is equation 2.44? Equation 2.44 states that what's up guys, it's me Sir Ernest, and today we're going to solve problem 2.43. What's up guys, it's me Sir Ernest, and today we're going to solve problem 2.34c of Griffiths 4th edition. So this is the third part of this problem, wherein the problem states that find the energy stored in a uniformly charged solid sphere of radius r and charge q. And we're going to do it in three different ways. So in this video, we're going to use a third method wherein equation 2.44 will be used. Okay, equation 2.44 states that the stored energy on this spherical shell, spherical solid charge or charged solid sphere of radius r is given by epsilon naught divided by 2 times the integral of surface. Yeah, this is a combination of two is the first is a surface integral, specifically a closed surface integral of V, that's potential, times the electric field, and that is your surface integral. And then we add it to a volume integral like this. So that's E squared. So this volume integral is happening over a certain volume, or t tau. So what is this volume? So in this case, we're going to take a spherical volume of radius A, wherein radius A should encompass our sphere. So that means A greater than R. And then later we're going to see what happens if A or this radius, the radius of the spherical shell would spherical volume would approach infinity. Okay. So what are we doing to how are we going to do this? Let's draw the spherical shell that we're talking about. So for example, this is the spherical shell where we want to calculate our uh, our integrals. Okay, so this spherical shell will now have radius A. So this has radius A, where A is greater than R. Okay, so let's do the integral one by one. So let's do this integral first. So let's start with the first integral, close integral over the surface. Remember, this is a surface, a spherical surface of V E dot dA. Okay, so at point A, at R equal to A, because we're looking at the surface, the potential at R equal to A is that this is 1 over 4 pi epsilon naught q over A. And the electric field at point A, the magnitude, would be equal to 1 over 4 pi epsilon naught times q over A squared. Because remember, this is just a solid sphere, and we already know that the potential and the electric field at a certain point away from the sphere is given by this. Okay, so we're going to use this here. So this is r hat. Okay, so let's do this here. So this is 1 over 4 pi epsilon naught q over A times 1 over 4 pi epsilon naught q over uh sige, okay. We don't do this first. So to try to um, let's do the integral first before substituting A. Okay. So this should be r squared. Be r squared. Okay, and this should be r squared in theta d theta d phi. Okay, so this part is this part. Okay, so from here we can cancel r squared, and then this becomes, so the result would be uh the result would be so 1 over 4 pi epsilon naught q, and then A can be taken out of the integral. So this is q squared divided by 4 pi epsilon naught squared times A times the integral of sine theta d theta d phi. So that's sine theta d theta and then d phi. This is a sphere. So the integral, in order for this to be closed, would be from 0 to what? This is 0 to pi, and this is 0 to 2 pi, which is 4 pi. Okay, so the first part would be equal to, so this one is equal now to, um, this is now equal to q squared, this just times 4 pi. Okay, so we can now delete this. Okay, so this is the first term. Second term, okay, so you will notice here that the electric field, this is the volume integral for the electric field for this configuration. So in this case, we're just going to do the volume integral within this spherical volume, okay? And because of that, we should consider this to be of two parts, namely the volume integral inside the sphere, spherical charge, and the volume integral outside the spherical charge. Okay, so that means if we're going to integrate this, this now becomes integral of e squared d tau inside, then plus integral of e squared outside. Mm, okay, so we already know that the integral inside this solid charge sphere uh, is given by what? This is given by, okay, this is given by, uh, so from the electric field before, so inside would be, this is integral of 1 over 4 pi epsilon naught q over capital R cube R. And then, yep, and then this is volume integral, so this is times R squared sine theta dr d theta d phi. Okay, and then outside would be integral of, outside would be 1 over 4 pi epsilon naught q over R squared. But remember, this should be squared, and it should be also squared. R squared sine theta d theta d, sorry, this should be, let me erase this. Okay, so this is R squared sine theta dr d theta d phi. Okay, so this becomes, uh, okay, this will become q squared over epsilon 4 pi epsilon naught squared, then R cube, then integral of R to the fourth, yeah, R to the fourth dr, and then integral of this sine theta d theta d phi. So this is 4 pi. And then this integral will be evaluated because this is inside. So this is r, r. Then plus this one. So this becomes q squared over 4 pi epsilon naught squared. And then this will be integral of 1 over r squared, right? Yeah, dr. And then again, sine theta d theta d phi, integrating over this sphere will give you 4 pi. So this is 4 pi. Now this dr integral, so this r integral or integral along the r is will be integrated from r to a because this is for outside. Okay, so that means this becomes q, uh, yeah, q squared over times 4 pi divided by um, yeah, divided by 4 pi epsilon naught squared times, so this integral will be r to the fifth over 5, right? Sorry, this should be r to the sixth. Sorry about that, because this is squared, so this should be r to the sixth. So this will be r to the sixth. So this is r to the fifth over 5. So this becomes r 1 over 5 r. Then plus this one. So this is q squared times 4 pi divided by 4 pi epsilon naught squared. Then times. So this is negative 1 over r integrated from, this is 1 over r, negative 1 over r, evaluated from r to a. So this gives us negative 1 over a plus 1 over r. Okay, so this is equal to, so combining everything, we now have, so then distributing this, so distributing this here and here. Okay, so 4 pi epsilon naught divided by 4 pi epsilon naught. So that's 4 pi epsilon naught in the denominator for both. And then still be curd will still be maintained. And then there's a 2 below. So this is now equal to 1 over 4 pi epsilon naught q squared over 2. And then this becomes 1 over a. And this becomes 1 over plus 1 over 5r. Okay, and then minus 1 over a, and then plus 1 over r. Okay, okay. So this is now equal to our result before. So that's 1 over 4 pi epsilon naught. Uh, this is 3q squared over 5r. Okay, this is the same result that we obtained in parts A and B, which tells us that whatever method that we use, we could see that we will arrive at the same uh, result. As you will notice as well that the taking of the size of the volume where we integrated the surface and volume integral is arbitrary. Okay? Because this is actually related to our previous examples. Now, what happens now as A approaches infinity? Okay, so as A approaches infinity, so that means the contribution of the firsts, this one, the contribution of this goes to 0. Okay, so that so what does it mean? It means that the resulting work done will now be equal to work done as A approaches infinity. So if we're going to integrate a whole the whole the we're going to make this volume spherical volume of radius A to be very, very big. The work done, okay, let's make this simplified. So the work done becomes this one. Okay, so this term plus this term. Okay, so you will notice that this becomes 1 over 4 pi epsilon naught q squared over uh, over 2. Okay, and then this becomes, yeah, this becomes Okay, yeah. So this becomes 1 over 5 r plus 1 over r. Okay, so this becomes 1/5 r plus 1 over r. So this is 6 over 5r. And then minus 1 over a. So this is the result as a approaches infinity. Okay, simple, right? Okay, so you will notice that uh, the work done, if we're going to take this integral, it would look like this. Okay, so that's it. That ends problem 2.34 of Griffith's 4th edition. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.